Good afternoon, everyone. My name is Qian from Shanghai Jiao University. I'm very honored to present our work Sensing to Hear Speech Enhancement for Mobile Devices using Acoustic Signals. Nowadays, the voice user interface or VUI is changing the way we search, shop, communicate, or even live. For example, we can use voice commands to control smart appliances. Meanwhile, voice message is becoming one of the most popular private communication modes on mobile phones. Where the voice input, especially mobile voice input, is easy to be disturbed by surrounding noises, which often brings users a terrible experience. A straightforward solution is using speech enhancement technology, which aims to remove noise from original audio clip and extract the clean voice signal. But traditional methods only use audio information, making them suffer from complex, noisy environments, especially when there are multiple talkers. In this paper, we turn our attention to the emerging acoustic sensing technology. We call this solution Sensing to Hear. In other words, leveraging acoustic sensing to help mobile phones hear more clean speech from the user. Specifically, we use the speaker of the phone to emit the inaudible acoustic signal and simultaneously use the microphone to listen to the signal reflected by moving lips. Based on this idea, we design our system, WaveVoice. WaveVoice is basically structured as an encoder-decoder network, in which the encoder layer takes as input both the acoustic sensing signal and the noisy audio signal, and the output layer will generate the enhanced speech. We use the phase and amplitude of the reflected signals as the sensory input. Moreover, instead of using a single frequency, we simultaneously transmit sound waves and multiple frequencies. We construct two subnets to successfully enhance the magnitude and phase of the time-frequency spectrogram. First is a magnitude subnetwork. We design a hierarchical scene which contains two individual scenes and one merged scene. Instead of directly outputting the enhanced spectrogram, we predict a mask and the hidden variables, and then multiply the mask with noisy magnitude spectrogram to get the enhanced magnitude. Unlike the magnitude spectrogram, the phase has very little structure pattern. To deal with this, we use the residual of the phase and the prediction of the network. Specifically, the phase subnetwork will take the enhanced magnitude spectrogram and the noisy phase as input, and use the phase residual and the hidden variables. We use a two-stage training to optimize our network. First, we only train the magnitude subnet. Then we fill the enhanced magnitude with the noisy phase to train the phase subnet. Due to user diversity, the performance of the enhanced network degrades obviously when it comes to a new user. So we propose a self-supervised method to personalize the universal model to the corresponding new user. The next part is implementation and evaluation. We develop a data collection app on an Android smartphone. The speaker and microphone are both at the bottom of the phone. 25 volunteers are recruited to participate in the data collection. Here is the dataset details. We also carefully generate the noisy speech by adding noises linearly to the clean speech. The noises contain both speech and non-speech noise. First, we perform an overall evaluation on our dataset. Following prior works, we evaluate the performance of WaveVoice merely under two metrics, SDR and PSQ. The figure shows that after enhancement, there exists a very obvious improvement on these two metrics. To show the importance of the acoustic sensing modality, we compare our system with three audio-only speech enhancement methods. As shown in the table, WaveVoice performs much better than any other audio-only methods. Then we evaluate the self-supervised mechanism performance on new users. It is clear in the figure that when the number of the new users' data is 200, the performance is comparable to that in the cross-validation. In the above evaluations, noises are added to the clean speech digitally. In order to investigate the robustness of WaveVoice in real settings, we perform evaluation with online noises. We use the character error rate and the evaluation metric. From the results, we can see that our system also achieves very good performance with online noises. Here is our conclusion. First, we unveil the utility of leveraging acoustic sensing to improve the mobile voice recording quality. Second, we propose a universal multimodal encoder-decoder architecture for speech enhancement. In addition, we design a self-supervised learning method to adapt the model to a new user. Third, we construct an audio sensory dataset and perform extensive offline and online experiments, which show the great effectiveness and robustness of WaveVoice. Thank you.